Okay, robot competition, learning, yay, people are excited about learning. Coding, Arduino, Mechatronics, wow, it kind of just likes to move these things all over the place in real time, great. Somebody is excited about the oscilloscope, cool. Oh, it lets you do emojis, I don't know what the ribbon is for. Capacitors. I'm guessing if you try to type in like a whole phrase or sentence, I don't know if it breaks it up into individual words or how this works. Integration, useful. Okay, I'm going to leave this open for another minute again just to make sure everybody gets a chance to type something in. Wow, I kind of wish this is a little hard to keep track of. There's a robot leg in there. There's the number 1. LeBron. Okay. So, again, I think like robot competition has kind of emerged as a clear leader here. And it's interesting to see that people are excited about things like high-pass filters and some of the more individual topics. Day end. You're excited for the data end. I don't know if those were supposed to be connected. Pocket. Okay. Yeah, kind of. If you're typing in phrases, is it like splitting them up into the individual words? Okay, so there's a lot of things. Try to do a single, or I don't know if you put it in quotes, if it'll keep them together or what. Okay, now the top is catching. Okay. Okay. I unfortunately don't watch much basketball, so I'm a little out of the loop on whatever's going on in the NBA, but I'm glad people are excited about LeBron. Okay, I am going to close that and attempt to move to the next one without accidentally showing the right answer on the screen. So I'm going to drag this off here for a second, deactivate that one, go to the next one. So fortunately this one is not as much fun. Activate. Which LEDs in the following circuit will light up? Okay, so this is repeated from the concept test. What we're going to be doing today is looking at how to use a breadboard. Again, with the collaborative idea that some of you already know how to use a breadboard and some of you do not. So hopefully you are kind of distributed randomly throughout the room. We're going to be using Tinkercad, but if you do know how to use a breadboard and you're sitting near somebody who does not, there's only one of me and I can't run around and get like into the middle of the seat, so you can kind of look over at their screen and help explain to them how this works. So I'll leave it. And there is, again, this is just for credit, there is an I don't know. Yes, do I have it as multiple choice so you can only select one?
Yeah.
Hold on, let me try and change that real quick. My apologies, deactivate, edit. So I have 2 correct answers selected, and I don't know why it won't let you pick more than one. So rather than trying to change the question type right now, let's just go pick, if it only lets you pick one, just pick one of the correct answers. Okay, don't worry about selecting both. Okay, so that should be activated again. And I will try and give us one of the hiccups I kind of figured was going to happen. Again, this is just for participation credit, so if you don't know, don't worry about it. If you think you know that there is more than one correct answer and it's only letting you pick one, just pick one of them. Okay, I'll leave this open for another minute-ish. And also, like, people in the back, can you see the breadboard well enough, or is this too small? Good if you can see in the back? Yes? Okay, thank you. Okay, another 30 seconds-ish. Yeah. 15. 5, 3, 2, 1. Deactivate. See the responses. Okay, so a lot of you got this right, some of you did not. If you didn't, don't worry about it, or if you don't know, the goal of today's lecture is to get everybody on the same page about how a breadboard works. So A and C are both correct, B and D are not because they do not have a closed circuit, as we will be explaining in a little bit. So I'm going to switch over to the third and final question for the day. I don't want to fill out a survey right now, poll everywhere, thank you. Okay, activate. This is trying out one of the clickable image things, so it's supposed to let you like click on a map to show where you're from or whatever. So you should be able to click. Again, read the question carefully and try not to just mash random places on the breadboard. Where could I move one end of the red jumper wire at the bottom? So we're talking about this part of the circuit down here. Where could I move that so the LED D lights up? Okay, and it looks like this probably isn't going to be that much more useful because it's just going to show a giant blob of points on top of each other right there. So I think most of you get the idea at this point. I'll just leave this one open for another 30 seconds. Give everybody a chance to respond. I did notice it shows the number of responses. I think that we have around 130 people in Canvas right now, so I'm not going to count how many people are in the room, but we're kind of ticking up towards everyone at the top right there. Okay, 5 seconds. Okay, I'm going to deactivate that one. Again, most of you got this right. We are actually going to switch over to the document cam now and introduce breadboards for a second before we use Tinkercad. Okay, so if you have not seen one of these things before, here's the deal. It's called a solderless breadboard. It allows you to prototype a circuit on solderless because you don't have to permanently solder things together. It lets you stick wires and parts into these little holes that are arranged in a grid to build a circuit that you can then take apart. And the idea is that it's easy to remove things if you make a mistake. The thing people have trouble with is figuring out which holes are connected to each other electrically. Like, so let me zoom in on this thing a bit. Oh, this is not it. So if you flip one of these over, you will see that segments of holes are connected by little metal clips, right? So you can see that there's a metal strip here. If I flip it back over, that means that these 5 holes are all electrically connected to each other internally by that metal clip, but the adjacent rows are not connected, right? So there's an insulator between, this is just the plastic case of the thing between these rows, and that's why in that multiple choice question, some of the LEDs weren't lighting up because there were wires in adjacent rows which are not connected. Okay, if you pop one of these out, so I brought this tiny screwdriver, you will see that these are, if I can really zoom in here, using the document cam always makes me nervous about like my fingernails or something good. Okay, if you zoom in, it gets a little grainy. See, these are little metal clips, so when you push a wire in there, the spring clip kind of pushes out and grabs onto the wire. And most of you took 3270 last semester, right? Solids, did you learn about fatigue failure? Okay, so these can break eventually. Normally, this is not a common failure point, but eventually these can, if somebody jammed a wire and then that was too big and then it doesn't clip back together all the way, or it's just a breadboard that has been in the lab for 20 years. So that is something to be aware of. If it kind of doesn't feel like it's a good fit and in there snuggling, your circuit's not working in lab or on homework. Again, it is rare. There are plenty of other things that can go wrong, but a breadboard can fail. A breadboard can also melt. If you don't know if you can see, these doesn't show up that well in document cam, but see how these 2 holes here are kind of a little more blobby looking than the nearby ones, because I had a short circuit on here at some point. So if you ever smell burning plastic, that is bad. Immediately disconnect the battery from your circuit. You probably have a short somewhere. Okay, and these come in all sorts of shapes and sizes. There are bigger ones in the lab. There are little baby-sized ones. But I should have mentioned that the different sizes, these strips on the side are called the power buses. These are usually connected the entire length of the breadboard. So see how this strip runs the entire way up and down. On some very long breadboards, it's broken into different segments in case you have multiple different voltages powering the circuit or something. And as we're going to see in Tinkercad in a minute, you usually use those to kind of make power available to your whole circuit, so you're not running wires from your battery pack or your power supply to multiple different locations. Okay, we are going to switch back over to the laptop, please. No, we don't with the document cam, hold on. And if you have laptop out, great, you should have already logged into Tinkercad, so please pull up Tinkercad. And we are basically, for the rest of the lecture, going to more or less start walking through QLab 1 with the goal of getting people who don't know how to use a breadboard comfortable using a breadboard, so you're ready to do that in the lab next week. So, again, you should have created an account for this already, so I don't want to spend 5 minutes with people logging in and creating an account for the first time. Once you are in Tinkercad, click Create, choose Circuits. That will give you a blank circuit with a random silly name, so you're going to be using this throughout the semester, so it's probably worth renaming things with names that make sense to you. So, for example, Breadboard Demonstration. Okay, let's give that a second for everybody to get it open. Try to get myself more screen real estate here. Maybe. All right. So hopefully this interface is pretty intuitive. Over here on the left in the big area, you kind of have just a workspace. Over on the right, you have a bunch of parts that you can drag out into the workspace. So we're actually not going to use the breadboard yet. I want you to just drag out a 9-volt battery, a resistor, and an LED. Okay, side note about resistors. How many of you are already familiar with resistor color codes and what the bands mean? Show of hands. Okay, so not very many. You will see more of this in lab when you pick up your individual kits, but long story short, resistors are really tiny. They are too tiny to print numbers on. So there is a colored band system, which frankly I don't have memorized. I always have to look it up, but there's a handy little table printed out where like brown means 0, black means 1, red means 2. I made that up, that's probably wrong, but you get the idea. So these bands, the first 2 numbers are the digits, and then the third number is a power of 10 multiplier. So this, for example, is a 1 kilo ohm resistor, which means, and so I had that, whatever. Brown is 1, black is 0, and red is 2, so it's 10 times 10 squared, or whatever the math is. So Tinkercad lets you just click on a resistor and enter a value. When you're doing this in lab, you have to figure out what value you need and then look at the color codes and figure out what the value is. Okay? So we're not going to worry about that for now. We are just going to build a basic circuit. I mentioned last time how the problem with electricity is that you can't see it, right? So LEDs are kind of a nice visual indicator because they light up when they're on. So if you're building a basic circuit, it kind of lets you know that your circuit is working. So without using the breadboard, I want you to just connect. So if some of you may have figured this out already, if you click on one of the terminals, it'll let you start making a wire. You can then connect it to the terminal of another part. So connect the positive terminal of the battery to the positive terminal or anode of the LED. That's the longer, kind of slightly curved leg. If you want to keep things neat, which another note for lab and throughout the semester, recommend doing, color coding your wires makes it a lot easier to debug things later. The standard convention is usually to use red for positive and black for negative, and then as you add more wires to your Arduino or something, you can choose colors for other, like blue for motor control, green for sensors, something. So it doesn't really matter what you pick for the other colors as long as you're consistent and you know what they're for. You don't just want to use black for everything or red for everything, because that can be a mess, okay? So we're going to talk more about diodes later in the semester, but LEDs need something called a current limiting resistor to prevent too much current from flowing through them and blowing them up. You'll see what happens, I think, if you do this in Tinkercad and say connect the LED directly to the battery and then hit the start simulation button up here. It does a little explosion icon. You can actually get these to explode in real life. I have tried on purpose, and the plastic will actually pop off, and it takes a lot of current to do that. Normally they just kind of flash and fizzle out real quick, so you won't actually see an explosion. And that is something that we're going to focus more on lab 2 on debugging and figuring out what's wrong in a circuit. I kind of mentioned, again, this last time, the whole thing about how we can't see electricity. With mechanical things, if something is broken or not working, you can usually see it or hear it or feel it, right? If something is vibrating, it shouldn't be. If you machine some parts and they don't fit together. The problem with a circuit is that if that LED just flashes real quick and goes out and you didn't see it, then you don't know the LED is dead, right? And you're just staring. If you're lucky, I shouldn't say lucky, but if there's actually fire or smoke or burning plastic smell, then you know something is really wrong, but that doesn't always happen. So in lab 2, we're going to talk more about, okay, the LED's not up. How do I know if that's because I built my circuit wrong or because the LED is actually broken? Anyway, you can delete a wire, connect the LED to the resistor, connect it to the battery, run the simulation, and your LED should light up. Okay, everyone got that? Again, if you're having trouble with the interface or something, again, I can't really run around in the lecture hall, but just check with the person next to you and try and get it going. Okay? All right. So great. That is just kind of freely wiring things together, which again, we don't want to do. We want to use the breadboard because you're not going to be soldering, or you could temporarily crimp the wires together with needle nose pliers or something, but that's kind of a lousy way to prototype circuits. We want to use a breadboard. Okay, so I'm going to delete my wires. We're going to practice kind of good conventions and stuff for using a breadboard, and then, assuming we have time left, we're going to talk about using a multimeter because that is something that historically people kind of have trouble with. So, again, there is no exact right or wrong way to do this and arrange the parts as long as the electrical connections are equivalent. I am going to kind of put my battery here next to the breadboard, and then again, I'm going to use the power buses. So this is a simple circuit with just an LED and a resistor, but excuse me, if I was going to add more stuff later, I want access to power throughout the whole circuit, so I'm not just going to run negative to a random row. I'm going to do things neat, and again, routing your wires. This is a little different in Tinkercad than it is in the real world, but in Tinkercad, if you just draw straight lines from point to point, then eventually they're all kind of crisscrossed and it can get really messy. So again, get in this habit early of kind of neatly color coding wires and routing them around so they're not in the way. And it's going to be the same thing when you're doing this in the lab. In general, you want the wires to be as short as needed to make a connection from point to point. Because if you have a bunch of long, really loopy wires, if you've ever heard the phrase spaghetti or rat's nest or something, that's just kind of what it eventually looks like, and it's impossible to trace them. Okay, so our goal is to connect the resistor in series with the LED. There are basically infinite ways to do that on the breadboard. Okay, the nice thing about Tinkercad is if you mouse over one of the holes, it highlights the other ones that are connected. So if you ever forget how that works, it kind of gives you a very visual reminder. You see the whole bus is connected. And again, then the gap across the middle is not connected. Okay, so it's just the sets of 5 holes on each side. So as I'll show you, there are actually, let me pause. I want you to try and do this yourself, okay, before I just show everybody how to do it. Connect the resistor in series with the LED so it lights up on the breadboard. Okay, and again, if you don't know how to use a breadboard, hopefully you're sitting next to somebody who does. Ask them for help. Okay? And I'll kind of do a lab and kind of gauge where we are. Based on everything I've told you so far, try and get it so the LED lights up using the breadboard. Yes. Remember, you do have to hit the start simulation button to make the LED light up, and then it locks the editor and doesn't let you drag parts around. So if you want to move something, you have to hit stop simulation, move the parts, and then hit start simulation again. Yes, walking around, I see some common beginner mistakes, but I'm not going to give them away yet.
Because these lines aren't connected to these lines. These lines are separate.
on to the light range of your screen. See that the LED is lit up. How much progress we're making. At the end of my second loop, I think I'll stop and take a loop.
I'm seeing well, this resistor may
I
be
see
in the wrong
a lot of people making this mistake, so I'm going to go up front and give you a hint as to what not to do.
Oh, you're so right. Yeah, got it. It's a little ugly. Yeah.
So, can anyone tell me what is wrong with doing that, the way I just placed the LED?
Oh, it's going to short circuit.
Yes, I heard that. So, remember, all of these holes are connected. If you put both pins of the LED in the same row, they are just short-circuited together. Okay, the same goes for the resistor. If I put the resistor like that is the equivalent, if I wasn't using a breadboard, of just wiring the resistor to itself. Okay, same thing for the LED. And you've heard current takes the path of least resistance, right? The current isn't going to flow through the resistor, it's just kind of going to take the short circuit through those metal clips. Okay, so I walked around, I saw a ton of that, not necessarily with the resistor, but with the LED like this. There is a rotate button up here, remember? So if you just kind of put it in the default orientation or something, that is your first hint. So I'm going to do another couple laps and see if people can figure it out after doing that. That's another thing to kind of play with. Okay, we've got some time, so okay, yay, we got it. Starting to see a lot of LEDs lighting up, so it's good. Remember that these holes are not connected across that gap in the middle. I think I just saw someone who had everything wired correctly on the left side, and the LED was over by itself on the right side. Also remember that the power buses are only connected along that vertical strip, and they do not magically bring power to whichever row you want. So you can use, many of you have figured this out, additional jumper wires just to connect 2 points on the breadboard. Okay, so for example, if I want power in this row, I can run a jumper wire from there to there, right? If I want negative or ground in this row, I can run a jumper wire from there to there. Okay, so the power buses don't sort of magically deliver power across that gap. And so I am kind of going to start putting this together. So if you're still super stuck, maybe follow my hint here in terms of how I have the LED arranged to see if you can figure out where to put the resistor. I'm also going to duplicate this and just show another way you could do it, because again, there's effectively infinite ways you could arrange things here. Okay, so neither one of those circuits is complete yet. If I hit start simulation, this is not letting up. And here's kind of two hints on two physically different, so physically arranged in different ways, but electrically equivalent ways you could do this. Okay, so I'm going to do one more lap, then I'll come back and finish this up, and we'll move on to using the multimeters. Come out of the stage list, you're still confused about how it works. This is an example of where when I mean the sort of component again, so you can ask in office hours, you can come up and ask me after lecture. There is a how to use a breadboard video on Canvas. So you're going to need to use this thing a lot this semester, so if you're still confused about it, we want to iron that out early on. Okay, I am going to complete these two, and again, this isn't how you have to do it, it is just two possible ways to do it. So copy and paste that. Here's one possible configuration. So if you kind of trace the path of the current, I have, again, positive, defined in physics as positive current flowing out of the positive terminal, even though the electrons are going the other way. We can't change the historical reasons for that at this point, but I can kind of trace the path through this wire, to the power bus, through this wire, to that row, through the LED, through the resistor, back to the ground or negative bus, and then back through the black wire, right? So if I hit start simulation, that LED should light up. And again, in kind of that concept test question, some of the LEDs weren't lighting up because it was not exactly like this, but roughly like this, where you had two adjacent rows, right? So now I have broken the path for current to flow. I don't have a complete closed circuit. That LED won't light up anymore. Another way I could do it, oops, didn't want to do that, there we go. To move this one, is say, for example, to make my LED or the resistor span the gap across the middle of the breadboard like that. So now these are not short-circuited together, right, because they're on both sides of that gap. But now I need to add jumper wires, I need power there, make that one red. And then the buses are not connected across the breadboard, right? So if you want power and ground on both sides, I need to run another jumper wire like this to connect the two ground buses. And I'm not using the power bus for anything on this side, so if I hit start simulation, yay, both my LEDs light up. I didn't mention LEDs. We'll talk about diodes later in the semester. LED stands for light emitting diode. They only let current flow in one direction. Think of it kind of like a check valve for water, right? Only lets current flow one way. So if your LED is backwards, if I go mirror that guy, it doesn't light up. Okay, so if, I should have mentioned that earlier. You could have had everything wired correctly, but just had your LED backwards. Okay, everybody good? Everybody have LEDs lighting up? Okay, next, using a multimeter. So, did you use multimeters in physics? Yes or no? Yes? No?
Yes.
Okay. How about this? Raise your hand, and not like the half-ass like this. Raise your hand so I can see it if you have used a multimeter before. Thank you. Okay, so a lot of you have used a multimeter before. Again, some of you haven't. We want to get everyone on the same page, and again, some people who have used them tend to use them wrong. So there should be a super simplified multimeter interface here. It just has 3 buttons. It doesn't have the dial with all the different settings like a real multimeter does. But same basic idea. It's got a positive and a negative probe. Connect it to measure the voltage drop across your LED. Okay, I'm not going to show you how to do it yet. Again, I'm going to kind of do laps and see if people know how to do this. If you remember how to connect a multimeter, how to measure the voltage drop across a component in a circuit. Okay? Connect the multimeter, start the simulation, make sure you have the little V button selected there to measure voltage, to measure the voltage drop across the LED only. Okay, so not the voltage of the battery, not the voltage drop across the resistor, just the voltage drop across the LED. Again, if you don't know how, ask somebody nearby. So the question after is it meant to be negative? If the voltage you get is negative, then just reverse your positive and negative terminals. Okay, so if you flip the positive and negative terminals, and I guess I will demonstrate this with the battery, for example, without showing how to do it for the LED. If I take the multimeter and just connect it, so notice how the orientation here, left, right, it has negative on the left and positive on the right. If I connect my power buses like this, and just kind of plug the multimeter directly into the power buses, it will give me just under negative 9 volts. So we'll talk about battery internal resistance and how that isn't exactly 9 volts at some point next week. But if I find my mouse again, if I swap those wires and go positive to positive and negative to negative, then I'll get positive 9 volts. And then this ties into the passive sign convention thing, which again we will talk about in more detail on Monday. But just like in dynamics, right, you define which way your positive axes are. Okay, if you define positive x to the right, and then you get a negative number for the x velocity, it means it's actually moving to the left, right? So kind of same concept with voltages and currents. So in that case, if you could redefine your positive x-axis to the left if you wanted to, or you say, okay, velocity is negative. So same idea here. You should connect. And if you go to the positively, the anode of the LED, and the negative cathode properly, then you should get a positive number. Okay. Let me do one more lap, just look at people's screens real quick, but I don't really hear as much talking or typing, so I'm guessing most people have this preview now. Okay, it should be around, I see like a 1.8, yeah, or 1.9-ish. If you change the resistor value, that voltage drop will change, but we are going to talk about that math. Yes? So the question was, how did I get the LED to connect across on the bottom there? I just made little additional jumper wires to turn them gray, so I faked longer legs for the LED. So you can't actually drag the LED legs themselves, but you can click one terminal of the LED and then connect the jumper wire to anywhere else, and I just made them gray so it kind of looks like the legs. Okay. So most of you, I think, have done this correctly, and again, there's more than one way to do it, but you remember from physics, to measure the voltage across something, you need to connect the multimeter probes in parallel to whatever you're measuring. So you connect the positive to one end, the negative to the other end. Again, this all ties into how the breadboard is connected. So for example, here I could go to the same row as the positive side of the LED, the same row as the negative side of the LED. It doesn't matter which hole in that row I go into here, because again, all those holes are connected. I could put this one there. Okay, great. I can start simulation, and I get the voltage drop across my LED. Great. Leave that multimeter there. Connect another one to measure the current through the LED. Okay. Second multimeter, measure the current through the LED. This is one that historically people usually have more trouble with. Got about 13 minutes left by my phone clock, so I think that should give us enough time to do this and all be on the same page going into lab 1. Again, if you are still confused about breadboards or multimeters, please ask for help, because I don't want you to just kind of struggle with the pre-lab and doing lab 1 next week. And I guess I should have clarified, leave that multimeter there, meaning don't delete that one, but if you need to move the wires for some reason, that's okay. So you should have two multimeters, but you don't literally have to leave that one approach exactly where it is.
Sorry, what's the next step? I already found the voltage.
Connect another multimeter to measure the current through the LED. Current in the multimeter, you need to hit the little A button. Don't leave it on the voltage setting. Now, take number one. The LED and the resistor are in series, so current through them the same or different? Same, right? So when I tell you to measure the current through the LED, in this particular circuit where I just have two parts in series, that is the same as telling you to measure the current through anything else. Okay, that is not always true. We'll talk more about series and parallel circuits next week. But in this case, saying measure the current through the LED, measure the current through the resistor, and measure the current from the battery, those are all the same thing because it is a single series circuit. Okay? We got time, 10 minutes left, so I'm going to do another lap. And then maybe come back to start getting some hits here. Okay, I'm starting to see some milliamp readings. Pretty good. Wires. Most common mistake people make when measuring currents is, when I say measure the current, I'm going to use this lower one as an example because it's a little easier to demonstrate here. They do this. I say measure the current through this LED. They will take their multimeter probes and do that. What is this multimeter? It doesn't let me change it into amps until I hit run. What is that multimeter going to display when I hit start simulation? 0. Why? Say it louder. I can't hear you up here. I'm deaf. Why is it going to say 0?
Because you're measuring the voltage drop over nothing.
Well, so assume I change it to amps once I start the simulation, but. So here the answer there was measuring the voltage drop over nothing. I'm also measuring the current just across nothing, right? Like a short-circuited connection there. So if I can start simulation, switch that to amps, I measure 0 amps because I just have the two multimeter probes short-circuited together. Okay, there is no current, no reason for the current to flow through the multimeter. Okay, if I want to force current to flow through the multimeter so I can measure the current through the rest of the circuit, I first need to break or rearrange the circuit, right? So I'm going to move this resistor down a row, Now I have an open circuit. So before the LED lit up, right, I still had a closed circuit for the LED, but the multimeter probes were short-circuited together. Now, if I move this multimeter probe down here, again, kind of trace the path of the current, now it goes through the LED. It has to go through the multimeter to get to the resistor. And so now if I hit start simulation, I get a current reading. And again, if you change the resistor value, or in my case, I have 2 LEDs, so the current's a little different than what most of you were measuring. But again, it's important for this to be clear because you can accidentally short circuit things and blow the fuse in your multimeter by doing this sometimes. Not necessarily by connecting the 2 multimeter probes directly together, but by forgetting to switch back to voltage after measuring current. And this doesn't really matter in Tinkercad because you're not going to blow up a physical part, but with your physical multimeters that have a dial, and the idea here is that current is literally flowing through the multimeter, okay? So whatever current is flowing through the rest of your circuit is going through the multimeter. If you connect the multimeter like I did before, directly to power and ground, if you have it set to measure voltage, that's fine. Voltage measurement, and again, we'll talk more about this next week. Think of it kind of like pressure measurement, right? Like a pressure probe. It can measure voltage, but there is no actual current flowing through the multimeter because it's connected in parallel. If you connect it in series like this, current's going to do it through the multimeter. So here, I don't know if Tinkercad will give me a blown up multimeter. Voltage is fine, but if I had set it to measure current and I forget to switch it back to voltage before measuring a battery voltage, you're short circuiting the battery. Right? All of the current from the battery is just going to go directly through the multimeter. So see how, this is the Tinkercad simulation does kind of model some real world things. I'm getting 6 amps out of the battery, which in real life, that's what's going to melt your breadboard and how you get the burny plastic smell, right? So it's short-circuited the battery. That is literally just like taking a wire and connecting the 2 terminals of the battery. There's no more current going through the LEDs. Everything is just going through the power bus. So that is another rookie mistake. It is generally safer to turn your multimeter off in between uses, and then the next time you hook it up, you set whatever you want to do. If you measure current, remember to turn it off or set it back to voltage as the default. It's not the end of the world. If I need to check with Dave Hartino about the models we have this year, but the fuses are replaceable, so it's like a few cents to replace the fuse. But the confusing part can be that, again, you might not see a spark or smell smoke or anything when you blow the fuse, and then after that, you're just going to get 0 for all of your current readings because the fuse is blown. So you could have your circuit wired correctly and hook up the multimeter and go, well, why am I getting 0? I swear everything is correct, and it's because you have a blown fuse in the multimeter. So again, that is another, if you're getting mysterious 0 readings and you swear everything is right, that is another thing to look out for kind of going into next week in homework 1. Okay, we have 5 minutes left, but I think I will just kind of reserve that for questions for people who still had trouble getting this to work. If you got it and you're good, you're free to go. If you have questions or you're still confused about something, I will stick around. Okay, thank you.